Hello, good evening, everyone. Welcome to the week 8 of this course, Digital Signal Processing and its application. So today is the tutorial session for the week 8, and today we'll solve some of the problem based on the week 8 lectures which has been taught in this class. And also this video will be recorded and it will be uploaded on YouTube, uh, and the link will be provided in the NPTEL portal, and anyone can access it anytime. And then if you face any difficulty, you can comment in the YouTube section also, and you can ask doubt here also in the live session. So now coming to our first question. Suppose we are designing a discrete time low pass filter for a voice signal with the following filter specification. The pass band edge is given as 4 kilohertz with 0.8 dB tolerance, and the stop band edge is given as 4.5 kilohertz with 50 dB attenuation, and sampling frequency is given as 22 kilohertz. So, and here H omega denote the filter frequency response. What is the approximate allowed range of magnitude of H omega in the pass band for which the filter meets the above specification? So a tolerance of 0.8 dB in the passband implies that the filter gain will lie between minus 0.8 dB and 0.8 dB. So this 0.8 dB tolerance means that, sorry, the filter gain in dB, that is 20 log to the base 10 H of omega, will be less than equal to 0.8 and will be greater than equal to minus 0.8. So divided by 20, we'll get minus 0.04. It's less than and greater than and sorry, less than equal to log 10 of H omega, and this is less than equal to 0.04. So magnitude of H omega is greater than equal to 10 to the power of minus 0.04 and less than equal to 10 to the power of 0.04. So when we calculate this value, we will get 0.912, like H of omega is greater than 0.912 and less than is equal to 1.096. So option number B is the correct answer for this question. Now coming to question number 2. In the previous question, suppose we choose to design a Butterworth filter following the design process discussed in the lecture. We have to first design an analog low pass filter. What will be the pass band edge, width of transition band for this analog filter? We have to choose the nearest option. So we have to find the pass band edge and the width of the transition band for this analog filter. The frequency specification of the discrete time filter here corresponds to the desired filtering effects on a signal that would be sampled before passing it to our designed discrete time filter. So what we have to do, we have to translate this frequency specification to the normalized angular frequency specification. So we have to translate frequency specifications to normalized angular frequency specification. So the normalized passband edge will be, let me check whether this video is getting recorded or not. So the normalized passband edge, yeah, it's recorded. Omega p is equal to, like that will be cutoff frequency divided by uh, sampling frequency. So fp passband is 4.5. Sorry, what is the given? We will write here fp is equal to 4 kilohertz, fs is equal to 4.5 kilohertz, and sampling frequency is 22 kilohertz. So omega p is equal to 4 kilohertz divided by 22 kilohertz into 2 pi. So after that we will get it will be 4 pi by 11. So this is the normalized passband edge. Similarly, the normalized stop band edge is equal to omega s, and that will be given as 4.5 kilohertz by 22 kilohertz into 2 pi. So it will be uh, 4.5 by 11. So if you multiply it with 2, it will be, sorry, we should not have cut it. It will be 9 by 22 into pi. So now for the Butterworth filter, this normalized discrete time filter frequency specification have to be converted to the analog filter specification. So first now we have to use the bilinear transformation. Using bilinear transformation, so the bilinear transformation here is given as omega is equal to tan omega by 2. Now hence the analog filter specifications will be analog filter pass band edge is equal to tan omega p by 2. So this will be our tan 4 pi by 22, will be 2 pi by 11. So when you calculate this value, you will nearly get 0.642. Now, analog filter stop band edge is equal to omega s, that is given as tan omega s by 2. So this will be equal to tan, it will be 9 pi by 44. So when you calculate this value, you will nearly get around 0.748. So the transition bandwidth, we have to find these two: analog filter passband edge, stop band edge, and the transition bandwidth. So analog filter transition width is equal to omega s minus omega p. Stop band edge minus pass band edge. So this we will get as 0.106. Okay. So which option is correct? 0.106. So transition band width is this one. And pass band edge, that is 0.6427. So what we got? Yes, we also got 0.642. So option A is the correct answer for this question. Now coming to the third question. Which of the following is true for the poles and zeros of the transfer function of analog Butterworth low pass filter? So the angle between any two consecutive pole is same. Yes, the pole of the analog low pass Butterworth filter, like Sk is equal to omega c e to the power of j n plus 2k plus 1 into pi by 2n. Here k is 0, 1, no, not n minus 1. So the poles of the analog given one, we can see that the consecutive pole have an equal angle of pi by n. So consecutive pole will have equal angle of pi by n between them. Okay. So option A is correct. Like the angle between any two consecutive pole is same. And they lie on us like this will lie on the semicircular path of radius omega c in the left half plane. Okay. So all the poles have a magnitude of omega c, and also the Butterworth filter transfer function does not have any zeros, hence the correct option are A and C in this question. Okay. All the poles lies on a path of radius omega c, and the Butterworth filter transfer function does not have any zeros. Okay. So option A and C are correct, because D is saying all the zeros have magnitude of omega c, so there is no zero of the transfer function. The angle between any two consecutive zeros is the same. So if there are does not have any zero, then how we can find the angle? So option B and D are not correct. Coming to question number 4, any low-pass analog Chebyshev filter can be completely described in terms of three parameters: n, epsilon, and omega p. And here the filter response is denoted as this. Cn, the function Cn is the nth order Chebyshev polynomial. A Chebyshev analog low-pass filter is designed to meet certain specifications. Suppose we need another low-pass filter with same specification, except for a tighter tolerance requirement in the passband. The new passband tolerance is delta 1 prime is smaller than the original value delta 1 with original filter parameters and epsilon omega p, and the new parameters n prime, epsilon prime, and omega p. Which of these must always be true? Assume that epsilon and n are always chosen optimally when designing the filter. So let delta 2 be the stop band tolerance for both filters, and let us define some quantities. So delta 2 be the stop band tolerance for both filter. Okay, so d1 is equal to 1 by, and d1 prime is equal to, and d2 is equal to 1 by delta 2 square minus 1, and d2 prime is equal to 1 by delta 2 square minus 1. Then the constraints on, like, E epsilon is less than equal to d1, and epsilon prime is less than equal to d1 prime, n is greater than equal to cos h of minus 1 square root of d2 by epsilon square, and cos h inverse omega s by omega p, and here n prime is greater than equal to cos h inverse of square root of d2 prime by epsilon square divided by cos h inverse of omega s by omega p. Okay, so as delta 1 prime is less than delta 1, so we have d1 prime less than d. So as delta 1 prime is less than delta 1, so it implies that d1 prime is less than d1, and epsilon prime are chosen optimally. We have epsilon prime is less than epsilon. As the stop band constraints have not changed, it implies that d2 prime is equal to d2, but epsilon has decreased to epsilon prime. So epsilon has decreased to epsilon prime. So the lower limit on n prime will be greater than that on n. So lower limit of n prime will be greater than that of n. Okay, but since n and n prime have to be integers, so it is possible that, so n is equal to n prime if both lower limits have the same ceiling. Hence we have n prime is greater than equal to n. And which option is correct? Option C is correct, because n prime is greater than equal to n and epsilon prime is less than epsilon. Now coming to the next question. Consider an analog low-pass Chebyshev filter with filter parameters n epsilon and omega p. The poles of this filter lie on which of these counters in the S-plane? Complex, analog. So this is the analog frequency domain, complex analog frequency domain. So in the question number 5, in this question, let beta is equal to 1 by n sine h inverse of 1 by epsilon, and let the kth pole of the Chebyshev filter given by Sk is equal to sigma k plus j omega k, where so like what we have studied in the lecture also, sigma k by omega p sine hyperbolic beta squared plus omega k omega p cos h beta squared is equal to 1. Okay, so this is the equation of ellipse, so whose axes are along the real and imaginary axis. So this is the equation of ellipse. So as cos hyperbolic beta is greater than sine hyperbolic beta, for real values of beta, and the semi-major axis is along the imaginary axis and semi-minor axis is along the real axis. As cos h beta is greater than sin h of beta for real values of beta, hence the semi-major axis is imaginary axis and semi-minor axis is along the real axis. Okay, so which options are correct here? Unit circle center at origin, this is wrong. Ellipse with major axis along with imaginary axis, yes, option B is correct. Ellipse with major axis along the real axis, this is wrong. Inclined ellipse with slope of major axis equal to tan h epsilon, this is also wrong. So option B is the correct answer for the question number 5. Now moving to the question number 6. Consider an analog low-pass Chebyshev filter with filter parameters are given and a transfer function Hs. Let the poles of the filter Pi, where I is 1 to n, like the n poles. Now suppose that all the filter transfer function is expressed as a fraction, where the denominator is product of S minus Pi. Which of these statements about Chebyshev filter and Chebyshev polynomials are true? So Cn minus x to minus 1 to the power of n. So this is in option A given, which can be verified to be true using these identities. Like we can verify this. So this function is given as cos n cos inverse of x when mod of x is less than equal to 1. It will become cos h n cos h inverse of x when x is greater than 1. Minus 1 to the power of n cos h n cos h inverse minus x when x is less than minus 1. So after verifying, we can find that it does not lie. We can verify in the range of minus 1 to 1 or minus 1 comma 1. So it does not lie. So option A is incorrect. Now for option B, C, D, we note that for odd n, like the function is for the value of x equal to 0 will become 0 for odd n. Now for even n, this value become 1. And also the transfer function hs is given as a by a is some real number. Here, so the magnitude of this transfer function square will be 1 by 1 plus epsilon square s by j omega p. So we see that for odd n, the magnitude, like for odd n, this value will become 1 by 1, 1. And for even n, this value become 1 by 1 plus epsilon square. Here we can substitute 0. And for a real filter, the impulse response is real, hence h of 0 will be real. In addition, we assume that h of 0 is greater than 0. Hence, we shall have h of 0 is equal to 1 for odd n, and h of 0 is equal to 1 by 1 and square root of, let's see, this will become h of 0 is equal to 1, and this will become h of 0 is equal to 1 by square root of 1 plus epsilon square for even n. So, a will be I is equal to 1 to n pi for n is odd, I is equal to 1 to n pi divided by square root of 1 plus epsilon square for n is even. Sorry, option A is the correct because as we can verify. So option A is correct, and option like for n is odd, the filter transfer function has numerator. So A is the numerator. So this will option D is also correct. There is a negative sign, so this is wrong because this is a negative sign, and this is also wrong because here epsilon is given. So it should be epsilon square. So option A and D are correct for this question. Now coming to question number 7. Suppose a low pass analog Chebyshев filter is designed with the filter parameters and beta is equal to 1 by n sine hyperbolic inverse of 1 by epsilon. In the figure, the line green makes an angle alpha k that is given with the positive real axis with k is 1 to n. The circle and the ellipse are all centered at the origin. The center of all the circle and ellipse are on the origin. So the inner red circle has a radius equal to omega p cos hyperbolic b, and so this you underline, and then the blue has its major and minor axis aligned along the imaginary and the real axis respectively. Is the semi-major axis has a length of omega p cos hyperbolic beta, and its semi-minor axis has length of omega p sin h of beta. Let ABC be the complex number corresponding to the points of intersection ABC respectively, which are marked on the diagram. Let the pole be given by sigma k plus j omega k. How is the location of pole corresponding to this angle alpha k determined? Select the option that is. So the pole of the Chebyshev filter are given by minus omega p sine ak sine h of beta plus j omega p cos ak cos h of beta, and here k is from 1 to up to n, and ak is equal to 2k minus 1 by 2n into 5. Okay, so this is again our alpha k is given as n plus 2k minus 1 by 2n into pi. So this is written as 2k minus 1 by 2n pi plus half. So ak is equal to alpha k minus half. Okay. And we can also see that a is equal to minus omega p sine ak cos hyperbolic beta plus j omega p cos ak cos hyperbolic beta, and c is equal to minus omega p sine ak sine hyperbolic beta plus j omega p cos ak sine hyperbolic beta. Since in the option B, the intersection of line with a smaller circle gives the real part of the pole, that is real part of PK is equal to real part of C. As you can see, that real part of like in equation given, PK and C is same. So option B is correct, and in option E you can see intersection of line with larger circle gives the imaginary part of the pole. So imaginary part of PK is equal to imaginary part of A. So option E is correct. Okay. So option B and E are correct for this question. Now, the question 8 to 14 are linked. So this section is dedicated to design the band pass filter whose specification will be listed in this assignment. Make note of this specification as the calculation that you undertake in this assignment will be used in the filter design sections of assignment 9 and 10. Now consider the problem statement. Let me drink some water. So given that analog signal is band limited to 160 kilohertz, and we wish to design a band pass filter in the discrete domain, unnormalized continuous time specification are described below. The pass band and stop band tolerance are 0.15 in magnitude. This is the filter magnitude response, not the magnitude required. So it is just the magnitude response. And must lie between 1 and 0.85 in the pass band and 0 and 0.15 in the stop band. The sampling, the analog signal is ideally sampled with a sampling rate of 330 kilohertz, and the pass band is from this to this, and transition band 4 kilohertz on either side of the pass band. So the first question is The given filter specifications are first normalized with respect to the sampling frequency. Which of the following are correct with respect to the normalized angular frequency specification in the discrete domain? Round off your decimal up to fourth place. So the pass band, stop band, transition band in normalized angular frequency domain can be found using the method like as we have discussed in the second question. So, so normalized frequency, sorry, frequency can be given as omega is equal to 2 pi f by fs. Okay, so here f is the normalized frequency and fs is the sampling frequency. So this is the unnormalized frequency and fs is the sampling frequency. Okay, and tolerance specification does not change. Okay, so the pass band will be, so pass band will be 85.7 divided by 330 into 2 pi. So let's use the calculator. So this will become and 205.7 by 330 into 2 pi. So our first one will become 0.51935 to 0.6406. Okay. So option A is the correct here. Transition band 8 pi on either side of pass band. This is wrong. Tolerance will be same. There will be no change in tolerance. So option A and C are the correct answer for this question. Okay. Now the next question is the normalized angular frequency specification in the discrete domain are then transformed to the analog specification using bilinear transformation. Which of the following are edges of the stop band in the analog filter specification? Choose the option within plus minus 0.03 of your answer. So the bilinear frequency transformation is given by tan omega by 2. Since we'll have the analog band pass filter frequency specification given by pass band is equal to 1.0629 to 1.5790, and the stop band, when you do the transformation you will get 0 to 0.9850, 1.7204 to infinite. Okay, so these are the stop band and the pass band. So here you can see which of the following are the edges of stop band. So the edges of stop band is 0.9850 and 1.7204. These two are the edges of stop band. So option C is also correct in this question. Now coming to the next question. The band pass analog filter is then transformed to a low pass analog filter using an analog frequency transformation. If the passband edge of the equivalent analog low pass filter is taken to be 1, enter the value of the stop band edge. So from the previous question we can see, so this is the bandwidth, or like where the passband will, for the passband of this, so this will be 1.0629 omega 1p minus 1.5790. Sorry, we have to subtract from the higher to lower value. So we will get 0.5161. Okay, and omega naught is given as the square root of omega 1p and omega 2p. So our omega 1p is 1.0629 into 1.5790. So the value of this square root will be 1.2955. So we are given the low pass analog filter passband edge is low pass analog filter passband edge is omega LP is equal to 1. And for the stop band edge, the low pass analog filter frequency transformation is given by omega L is equal to omega square omega naught square divided by B of B omega. Using the transformation, we get initial value for the stop band edges of the low pass filter as omega 1 ls. Like after this transformation, what we will get? I'm just writing the answer. You can transform omega is equal to minus 1.3929 and omega 2ls is given as 1.4432. So however, we can only choose a single stop band edge to design our low pass filter. So we can choose single stop band edge to design low pass filter. So when deciding the stop band edge for the low pass filter, we need to ensure that the tolerance conditions are satisfied for both the stop band edges. Now, either a monotonic or equiripple stop band using a Butterworth or a Chebyshev filter, the magnitude of the filter frequency response does not increase beyond the value at the stop band edge. So here we should choose the low pass filter stop band edge as omega ls as minimum of omega 1 ls comma magnitude of omega 2 ls. So what is the minimum value? So that is equal to 1.3929. So the stop band edge required is 1.3929. So here for question number 10 it will be 1.3929. Now coming to question 11, suppose the magnitude response in the pass band and stop band is monotonic. Enter the minimum order of the Butterworth filter that can be used to design the filter and meet the desired specification. So, like in question 4, we have already like defined D1 and D2. Here you can see, or I can write there only directly. Our D1 is equal to 1 by 1 minus del 1 square minus 1 and d2 is equal to 1 by del 2 square minus 1. So when you substitute this value, you will get d1 is equal to, because we have given the values of tolerance, that is 0.15 in the magnitude. So we will get d1 as 0.3841 and d2 is equal to 43.44. Okay. So the n is greater than log of d2 by d1 divided by log of omega ls by omega lp. So when you substitute this value, you will get, we already have omega ls and omega lp. So finally, after substituting all the value, we will get 7.1341. So what should be n? N should be greater than or equal to 7.13. So n is equal to 8. So we have chosen the value n is equal to 8. Now coming to the next question. For the Butterworth filter with the minimum order n calculated in the previous question, that is n is equal to 8, which of the following values of cutoff frequency can be used to design the filter? So, the constraints on the cutoff frequency parameter omega c, like omega c is given as Already we have all the parameters omega LP, omega LS, D1 and D2. We'll substitute all these values in this. So after substitution, we will get 1.061 is less than equal to omega 6 and omega C is less than equal to 1.1004. So here in this question, like it is up to 4 digits. So we have to find which of the following values of cutoff frequency can be used to design the filter. So 1.0619 can be used because it lies between the limit 1.0616 and 1.1004. 1.03 does not lie in the limit. Now again 1.07 can be used and 1.12 also does not lie. So which are the correct option? That is option number A and option number C. Okay. Now moving to the next question. Now suppose the magnitude response is equiripple in the pass band and monotonic in the stop band. Enter the maximum allowed value of Chebyshev filter parameter epsilon that can be used to design the filter and meet the desired specification. So in the case of Chebyshev filter, the upper limit on E is given by is square root of D1, which is obtained by observing the minimum passband magnitude. Response value is 1 by and minimum passband magnitude response value is equal to 1 by square root of 1 plus epsilon square. So which cannot be less than 1 minus delta 1 and delta 1 that is a passband tolerance. So in this question, epsilon is less than or equal to 0.6197. Okay, because the 1 by 1 plus epsilon square should be greater than 1 minus delta 1. Now delta 1 is the passband tolerance. We can substitute the value. After substituting, we will get epsilon should be less than equal to 0.61. Enter the maximum allowed value it's asking. So epsilon will be 0.6197. Okay. So the maximum allowed value is 0.6197. Now coming to the last question of today's class. For the Chebyshev filter, with epsilon as calculated in the previous question, enter the minimum possible order of the Chebyshev filter. Minimum possible order required to meet the desired specification. So for a Chebyshev filter, by observing that for a monotonic stop band, the stop band magnitude response is always less than its value at the stop band edge. So and this value has to be less than or equal to del 2. So the n should be greater than equal to cos h inverse square root of d2 by epsilon square. I think we have did this in question of 4 or 6. Cos h inverse omega ls by omega lp. So now the for chosen epsilon, what is the epsilon value in the previous question? 0.6197. And we have the value d2 and omega ls and omega lp. So this value will become 3.55. So what is the minimum possible order? So minimum possible order of the Chebyshev filter is n is equal to 4. Okay, so for today we'll solve up to here only, and we'll meet in the next class at the same time between 7 to 9. So if you have any doubt, you can ask. And also this video will be uploaded on the YouTube. So you can ask your doubt in the comment section there. And the link will be provided for this video on the NPTEL portal. So today we will bind up here only. We'll meet again in the next lecture. So thank you everyone for attending. So today we will bind up here only. We will meet again in the next lecture, and this video will be uploaded on YouTube, and link will be shared in the NPTEL portal. So thank you everyone for attending today's lecture. We'll meet again, and let me check whether this video was recorded or not. Yes, it's recorded, so it will be uploaded on the YouTube, and link will be provided in the NPTEL portal. You can ask your doubt in the YouTube section also if you missed this lecture. We can clear there whatever doubt you have. Thank you.